So the objective of this lab was to select a real brush DC motor encoder and planetary gearhead from Moog Motors for the purpose of driving a theoretical automated warehouse vehicle. This theoretical vehicle would be capable of transporting packages of up to 200 pounds and would weigh in about 45 pounds. So when we applied a 15% overhead for safety, this comes out to 7.95 newton meters of continuous torque at each wheel, which is our load. For component selection, we chose the C34L70 with winding code 10. The C34 family of motors from Moog is I guess you can think of it as their middleweight class of motors in terms of weight and performance. So the C34L7010 is pretty unique in Moog sells a lot of motors, but this one is definitely unique in that it has a very high rated speed as well as a respectable amount of torque. The speed is its defining characteristic because 44,450 RPM is significantly faster than any other motor in its own family, this other C34 motors, as well as it's a lot faster than a lot of the other motors as well. It only has a terminal voltage of 24 volts, which is workable. Since our motor already has a decent amount of torque and we have really small wheels, so the load isn't actually that much per motor, we don't really need a very large gear ratio for our gearhead. So we chose the 16:1 planetary gearhead, which is the bare minimum that we needed for this project. As for our encoder, we went with the HEDM 5500 because it has the highest resolution at 1024. This is important because our robot's going to be transporting heavy objects around a warehouse in close proximity to human workers, so precision of movement's really important. We want to know exactly what position, what speed our motor is at. Alright, on to the Simulink.
So our overall Simulink block diagram is shown. We have a simple step response input of our desired speed. So a value of 1 is equal to 1 radians a second because our speed is in radians a second for this model. When going on to the PID, so our PID, we use a PID because we wanted to have 2 zeros to control the root locus desired at our desired location. Going on to the PWM generator, I designed my own PWM generator using a comparator of a triangle wave and a constant value. When the constant value is at a higher voltage, the PWM output is actually smaller. So duty cycle of if a voltage of 17 volts is entered into the system, the PWM output would be a 17/24 ratio, and that would be the duty cycle of the PWM generator. So that goes into our simple DC motor, and it takes the average voltage that is being input into the system and converts it into a speed. We use the A and B channel of the encoder to output an HFS for our system. The HFS for our system was made by using an instantaneous velocity measurement. We use a quadrature pulse wave to represent the A and B channel. So it is twice the frequency of A and B, and twice the frequency of the A channel and the B channel. The sample and hold block represents the counter, the counter measured count value of the counter. The counter is a free running counter and measures only the on time of the pulse wave, of the quadrant pulse wave. So that means it's a half cycle measurement, which is another factor when converting it to a gain. So when we convert it to a gain, we know that the proportionality of counts is related to time. So we need to have 1 over time, uh, because time is inversely proportional to speed. That's why when we go to the h of s gain block, that's why we see this proportion 1 over the inverse of the count value. The k gain represents the formula provided here. Omega is equal to 2 pi f over nm. So we see that f is equal to clock frequency, m is number of clock cycles, n is pulse rotation. We know the clock frequency based on our sample and hold time, sampling time at 1 megahertz. And we know that the number of clock cycles is represented by the sample and hold count value from our free running counter. So that goes into that is inversely proportional. So it is divided here. And the pulses per rotation is 1024 times 2 because of the quadrant pulse as well, and then multiplied again by times 2. So it's time. So the number of pulses per rotation is 1024, which is the resolution of the A and B channel, times 4 because it's a half cycle, and it's twice the frequency of the A channel. So going on to the Simulink model, that represents the h of s. That's the instantaneous speed. It goes into the summary injection because we want to know the error from our desired. And that's the reason, and we chose and this is how we implemented the instantaneous velocity h of s into our system. So now we're going to explain the PID, now we're going to explain the
Precompensation
PID
oh.
characteristics.
Alright, well, before the PID, I'm going to talk about what our system, or the behavior of our system prior to adding any compensation or control. So this is the GP of S, or the transfer function of our plant. It's important to note that this isn't just theta S, this is theta dot S, or derivative of theta. So what this means is the transfer function for our plant doesn't represent the position, the rotational position of the shaft of the motor as the standard transfer function does. It represents the rate at which the position changes, or speed. So we used MATLAB, as you can see here, to obtain the characteristics for the motor transfer function. We can see we have one pole at negative 31.45, damping constant of 1, and omega n of 3.14, or 31.4. And now that we have our G of S, it's pretty simple to get our closed loop T of S using the standard form G of S over 1 plus H of S G of S. And that gives us T of S equals 4.875 over S plus 10.431 as our closed loop transfer function. You can see that we have no zeros and only one pole at negative 10.431. So without control, there's really not much we can do here. This is the root locus generated using SISO12, of course, as well as the base characteristics also generated using MATLAB. So the goal of our controller initially was to improve the following parameters. Settling time should be improved by 20%, peak time should be improved by 15%, and we're looking to remove steady state error and minimize percent overshoot, specifically keeping it under 5%. So settling time and peak time are both functions of zeta damping factor and omega n natural frequency. So the objective is to find a zeta and omega n pairing that will fulfill our desired settling time and peak time specifications. So getting omega n as a function of zeta, we substitute that into the desired T of S equation, and we get this polynomial at the end. The solution to this polynomial is a complex conjugate, which means that there's no pairing of zeta and omega n that can give us all of our desired characteristics. So if we can't get T peak and T settling, we had to settle for one. So we chose for T peak. So our updated objectives, or what is actually achievable for our system, would be improving T peak by 20%, minimizing percent overshoot, and again, removing steady state error. So in order to obtain the operating point, we begin with zeta as, I guess, a starting point, because percent overshoot is a function of only zeta, and we can use zeta to obtain beta, or the angle of the operating point. With zeta, we can also obtain omega d, which is the complex component of the operating point. And using those values, we're able to obtain a desired operating point of 121.17 at 15.2 degrees in polar form, or 116.93 plus 31.77 J in polar form, in Cartesian form. All right.
In order for us to achieve our desired responses, we're going to be using a PID controller. So the PID controller gives us two zeros and one pole. So one pole and one zero are going to be used for removing steady state error, and the other zero is going to be used for manipulating the root locus. So here we can see the locations of the poles and the zeros. So there's one pole near the origin at negative 0.18. There's two zeros at negative 89 and negative 218. Here in the root locus, we can see the two poles. So one pole was from the original transfer function, the open loop one, and the other pole is the pure integrator. So we can see that the zero is drifting towards 180 degrees, and the two poles are going to collide and then break away. And their breakaway angle is constantly changing because they're attracted by the zero that's drifting to the left. And we can see that the pink dot represents our operating point. So, which means we were able to achieve our desired responses.
So this is like cut off now that I'm looking at it. But yeah, it's mirrored across the real axis.
And here's a step response.
Yeah.
Go ahead, Oscar.
So our response was, all of our requirements were met by this response, and we felt that we could just implement this directly into our control system block diagram, as we did here. So I'm going to talk about how we found the proportional, integral, and derivative gain. We used the compensator in MATLAB to find the pole locations. And we found the pole locations and the entire gain of the PID. So the big K is 0.60318. That's it. That's the entire gain of the compensator. And we use this equation to find the exact proportional gain, integral gain, and derivative gain. So because we know that all the k's are related to one another, as we see here, k1 over k3, when we multiply the pole locations together, we get s squared plus k1 over k3 times s plus k2 over k3. So since we know what k3 is, then we can easily solve for k1 and k2. K1 is proportional gain and k2 is integral gain. So and k3 is the derivative gain. So we found the desired gains of the PID, and we plugged it into the MATLAB block PID controller.
Alright, is that it?
That gave us the closed loop response of the system. Can we look at that?
Yeah. You want this or the air signal?
I want the instant speed.
Ah, damn.
So the H of S, this is the H of S of the system. And can we open up data? Data dot. And this is the C of S. So this is the actual output of our system. And we see that H of S and the C of S of our system have the same response, meaning that we have correct feedback, and we are and that our error signal is being compensated in our PID to meet a desired step input of 1. The overshoot was not expected in our closed loop Simulink model because our root locus design didn't have a overshoot of almost
50, more than 50%, almost
more than
100,
50%.
75-ish.
Yeah.
So we would we would want to better design our system to meet our requirements. However, our mathematical model for our system was not as accurate as we had thought. However, we do meet no steady state error because we do meet the step input signal desired.
Shoot, sorry.
I would like to note that the HFS was found by implementing an open loop response first before testing in closed loop, because testing in open loop would be the actual we would actually know if the HFS is correct, because the HFS is crucial to understanding the actual motor speed. So I tested first with an open loop, and then once I knew that the HFS matched the actual motor speed, I used it in our closed loop system. So that concludes our closed loop response and Simulink design of our autonomous vehicle power motor speed controller.
Yeah, I think that covers everything.